toys. So again, that is a strong magnet, so keep away from your laptop, from your mobile, and things like that. And you can make this fall experiment. And at least I remember when we did that at physics school, there were a normal magnet, not this kind of super fancy, super strong magnets. And you have had to take a watch to measure the difference in falling speed. But the funny thing is, if you have a proper magnet, you can now, watch it going through, and you can count and count and count, and you can see it from top nicely moving down, and it takes quite a while, so it's really slow. So it's a very nice experience. So I give it through, you can look yourself how it floats down. And so, have fun. So, again, we are in this kind of complicated diagram of all the different processes we want to discuss, which are all related to magnetic fields. And you saw already that diagram from before. But now, what I want to do in that lecture is to speak a little bit about the magnetic field on even larger scale. So before we spoke about these magnetic fields inside these galaxy clusters, which you see here as a point in the rotation measurement maps. But now we can discuss a little bit if there are possibilities to constrain or to measure cosmic rays here in this filamentary structure or even in larger structure. So this kind of lecture should, so to speak, stay in this kind of phase space here, just discussing about magnetic field itself and about rotation measurement again a little bit, and then even a more very current topic, propagation of cosmic ray ultra-high energy cosmic messenger particles, meaning either charged particles or even photons, and what we can learn on magnetic fields from that. Okay, so again, little bit of introduction, then some discussion on Faraday rotation measures, and that is especially here the kind of negative discussion, because current observations also first they indicated that you might see something, makes it, due to the uncertainties in the measurements, still quite impossible to infer something, but I think for future instruments that might be quite interesting. So that's the reason why it's added in. And then there's this very new topic where you have ultra-high, very high energetic photons, which do an electromagnetic cascade on the way to us. And in the phase of this electromagnetic cascade, they can be deflected by the magnetic fields, and you get different observables of your source. And so I want to go through that. So why is that interesting? The reason is, and again I will show you that more of that in one of the next lectures. Inside galaxy clusters, you have this kind of very turbulent atmosphere, which is dominated by the merging. And as shown by various authors, it's almost independent on what source of magnetic field you plug in. As soon as it has a kind of reasonable seed strength, the process will amplify and stretch and orient the magnetic field so that it's compatible with what you observe, because you at a certain point go into a kind of equilibrium between the magnetic field amplification and the turbulence component. So, but if you go to larger and larger scales, there are some remains, or you hope at least you'll be able to find some remains which indicates or which gives you links on the source of the magnetic field, so where the cosmological magnetic fields are coming from. And that here is from a set of simulations done by Dolag et al. In 2009, where a cosmological simulation is done here. So that is roughly 80 megaparsec across the box. You see the cosmic web, you see the galaxy clusters, and what is just shown is the projected magnetic field. And you can see what is the difference if you start from a primordial magnetic field. So you start from a space-filling magnetic field at high redshift. Let the simulation evolve to today. You see the magnetic fields in the filaments, in all the collapsed structure. Or alternatively, at that time, what was done is you could hold the simulation at early times, say redshift 4. You identified all the galaxies in that simulation, and you placed a small dipole field in all of these galaxies you you resolved, and then you continued that simulation. So you start with zero magnetic field till high redshift. When first galaxies are formed, you plug in magnetic fields only in this halos of these galaxies, and you see how the magnetic field gets distributed. And that is just for various different parameters of these kind of modelings, like the field strength, the shape you put in, or if you even hold the simulation several times to find new formed galaxies and put in also their magnetic fields. And the important point here is that these kind of different models all give approximately the same magnetic field in the galaxy clusters, but as you can see in the large-scale structures, in the filaments, in the void, is much different. If you have it from the galaxies, and again, these are very simplistic simulations, they don't include any explicit galactic winds, so the magnetic field cannot be transported outside the galaxies, they just get mixed in the ICM by interactions. And what you can see is that in that case, the magnetic field is really constrained. You have only magnetic fields inside collapsed structures, right? So in this kind of diffuse filaments, you barely find magnetic fields. Whereas if it would be primordial, you would have everywhere magnetic field just with different strengths. And that's even more true here in these voids, as you can see. So also you barely see something in this kind of primordial models. Of course, you have magnetic field in these voids, although it's low. It's almost at the level of the magnetic field you injected, just scaled by adiabatic compression or expansion, whereas in these models you don't have. So the question is, can you distinguish this kind of different models? And for example, if you look at models where magnetic field is seeded by AGN lobes, then you would put magnetic fields only basically in the center of the very massive structure, not in the dwarf galaxies, so you would get even different magnetic field distribution. And the question again is, can you find some way to measure that? So another way of looking at these different models is a plot like that. So here's plotted the overdensity, so the density in units of the mean background density of the universe. And here's the magnetic field strength. So if you have a pure primordial field with no additional amplification mechanism, you would just expect this line, which would correspond to an adiabatically frozen-in magnetic field. So in underdense region, you get a depression. In overdense region, you get some compression and amplification. And then if you look at different models for this magnetic fields, you get an amplification in cluster centers. So in this terms of overdensities, the center of the cluster is usually at 10 to the 4, 10 to the 5 times denser than the mean universe. Then at the outer part of the halo, you add several hundreds of the density, and then you go to filaments and sheets, which are ordered at something like 10-ish in overdensity, and then you go into voids, which are even slightly underdense. And again, you have here different models where you plugged in different primordial seed fields, like these three, or different models of galactic winds. And what you can see is that they have slightly different shape, but here in the cluster region, beside of this very weak model here, which didn't have enough amplification at that time, you reach almost the same magnetic field in the cluster. But again, here outside in these voids and filaments, you see significant differences. So here you hope you can really learn something. And just if you want to explore observations, you might also take these kind of models and then just artificial scale the magnetic field to produce models which even have very high magnetic fields in this filament and void region, just to take into account that might be there are some plasma physics effects in these shocks which are around even the filaments or things like that which are producing magnetic fields, or your simulation don't resolve the turbulence in these regions. So that is just some toy models. So you take a normal simulation and then you produce some scaled models here just to allow to have high magnetic fields in this low density region, just if you want to test some observations, what is the probability to detect things. And what you can see here especially is, as you want to scale these models in a way that you get the same rotation measurement signal from galaxy clusters, you cannot just shift them up, but you really have to tilt them. So if you have higher magnetic field in the center, to compensate that, you have lower magnetic field in the outside, and vice versa. So if you push the magnetic field to the outside, you have to lower the magnetic field in the center so that the integral roughly stays the same. Otherwise, you get incompatible with rotation measurements. So these kind of models are kind of synthetic and toy models to test your different aspects. Now, basically, I want to talk about 3 different processes here, which are summarized in this kind of sketch. So first is, again, as we have had before, rotation measurement. So you have a polarized source somewhere at high redshift, and the polarized radio emission is traveling through the cosmic web and gets deflected. And this time we might even not look at sources which go through center of galaxy clusters, so where we get a very clear signal, but we might want to look at stuff which just goes through filamentary regions. So we might have to do statistics to measure an actual signal. Again, the problem is that the signal will be proportional to the magnetic field times the density. So if you go to lower density regions and you expect the lower magnetic fields, then as you can imagine, that's always a kind of higher penalty, because it's not only that the magnetic field is lower, but also the density is lower, so your signal decreases even more. Second possibility is you can look at propagation of high energetic cosmic rays. For example, you have high energetic cosmic ray protons. The problem here is that we still don't know where they come from. So we measure them on Earth, but it's not clear what is the source of these ultra high energy cosmic ray protons. So you observe a proton in a certain direction. It might have been deflected by the magnetic fields in filaments and voids. But as you don't know what is the source, again, it's very difficult to measure that deflection. So you have to model both things. So one idea is that if the deflection is quite small, you might be able to still identify the source, and then you get very good information about this deflection. If the deflection is larger, then you have to do some statistics to infer kind of mean deflections and things like that. But the good thing is that deflection only depends on the magnetic field. So this measurement, of course, will be smaller as the magnetic field is, but you don't get this additional penalty from the density. So that is already much more sensitive than these other measurements. And kind of third class of models, which breaks up in 2 kind of sub-processes, is if you have a gamma ray, very high energetic gamma ray, and here again you know the sources, and the gamma ray, of course, can just propagate to you, nothing happens, but some of them are doing an interaction with extragalactic background light. They produce this electromagnetic cascade where you have charged particles. They can be deflected by the magnetic field, and they make you, at the end, by again a Dassler interaction with CMB photons, make secondary gamma rays, which you might observe. So this kind of process can leave on that you get the gamma rays directly from the source, but you get also some gamma rays which you would see as a diffuse halo around the source. So you will get a kind of diffuse halo of lower energy gamma rays around your high energy gamma ray source, and the size and the intensity of that halo is reflected by the magnetic field. And again, the good thing is that is depending on the magnetic field alone. So it's again very high signal, and also it depends on the total length traveled. So for these kind of processes here, it's always equivalent. If you have one strong magnetic field here in between which deflects the cosmic ray protons, you're just dominated by this one strong deflection. In these kind of processes, this kind of electromagnetic pair happens everywhere along the line of sight. So if you then measure something, it always reflects the mean magnetic field along the line of sight. So that is really giving you a measurement of the total magnetic field all along the line of sight, whereas here you always have the degeneracy that you can have one region of the space, like a filament, which has heavy magnetic field and does a very strong deflection, and all the rest is doing no deflection. Whereas here, again, it's really a nice measurement of magnetic fields which have to be present all the way. If you have significantly part of that way not magnetized, you will significantly change the signal. The second subclass of this kind of things is, again, you have this high energy cosmic ray, the high energy photon, which would arrive the observer, and this electromagnetic cascade is scattering these photons out of the way, right? So that means that if you would have no magnetic fields, the secondaries would also just come from the same direction as the primaries. So you would see a point source with this lower energy tail. And as strong as the magnetic field is, as more of the secondary you are deflecting out. So this is a way to, if you look at the spectrum you observe, and you look at the low energy tail, the presence of the low energy tail is telling you how much of the photons are scattered out. So what is the magnetic field along the line of sight? And again, the signal is proportional to all the magnetic field along the line of sight. It doesn't matter if you have a region with a high magnetic field in between, the region with the low magnetic field contribute as well. So if you do that more schematic, then look at these different processes, then again, rotation measurement is still most sensible to the high density regions, like in clusters we have seen in lecture 1, but we now try to extend that a little bit further out, but still it's here at the micro or a little bit sub-microgauss level. But if you go to the ultra-high energy cosmic rays, this kind of deflection here, that is typically sensitive to magnetic fields of 10 to the minus 9 Gauss. So that's significantly lower than what you can detect with rotation measurement. And if you go to this TV gamma rays and to this cascade things, then you're typically sensitive to magnetic fields which are even 10 to the minus 14-ish or 10 to the minus 16-ish even. So that is really an extreme new window currently opened to measure extremely low magnetic fields. And here again, the nomenclature is different, because from people working on clusters, you would call that extremely low magnetic fields. For people who are working on primordial magnetic fields, 10 to the minus 14 is extremely high. So you have to keep that into account when you read the title of the papers. Yes? Yes. No, then basically you go down from TV to GV, and below that you have different processes. I show in detail more. It's just kind of overview what should come. Okay, so first part, let's have a look at rotation measurement. Again, remind you that, so to speak, constraining high density, high magnetic field regions, because the signal is proportional to density and magnetic field. Now, recently, there was published a very nice catalog by Taylor et al., which is a kind of full sky map, as you can see, with some holes, which now are partially filled by Australian measurements, but that is still the original data here. And every point here on this map is one polarized emission of a background, mostly backgrounds, quasars, or radio galaxies. And the color is telling you that the rotation measurement towards this source is either positive or negative. And the size of the circle is telling you how big the rotation measurement is. Okay? So, looks very beautiful. And of course, the idea is you could use this kind of data to constrain how much of that rotation measurement is coming from your large-scale cosmological field. Your problem, however, is that, as you can see, all the dominant structure you see here is your galactic foreground. So you have to deal with galactic foreground and with the measurement errors. Nevertheless, there was a claim in 2009 that using these clusters, these simulations, and using calculating correlation function, you could constrain a cosmic magnetic field to be 3 times 10 to the minus 8, which is extremely high if you in terms of a mean cosmological field, right? So it was interesting to check how good these things is. Now, again, to emphasize what is the signal you're looking for and what is the foreground you want to dig out. So that are rotation measurement maps of all these different magnetic field models I showed you before. So there are the ones which are the real simulation, and then there are this kind of toy models with extremely high magnetic field. And that is the galactic foreground. And you can, again, plot that either as this kind of maps, or you plot that as a rotation measurement distribution. And again, you can see that you are basically dealing with a signal which is several orders of magnitude below your foreground. So it's really difficult to extract the signal, and you have to be very, very careful. Now, what you can do is you can take a cosmological simulation, and in this case, it's a cosmological simulation which is constrained to reproduce the local universe. I will show you in more detail how that looks like. And what you need is you need to predict the position of the galaxies. So you take the halos in your simulation. You need the magnetic field, and you can test, again, different magnetic field models. And you try to do the kind of full analysis and try to see this kind of correlation functions. Now, you have to model the galactic foreground for that. So there's, for example, here a very simple model of the galactic magnetic field. You can plug that into codes like Hammurabi, which is a publicly available code which allows you to model the galactic magnetic field and produce you full sky maps and deflection maps and radio emission maps. And in that case, we used it to produce rotation measurement maps. So you have a model of the foreground. It's not perfect. As you can see, the difference between here's this foreground model and the data is reflects our uncertainty in modeling the galactic magnetic field. Meanwhile, there are better models with much more free parameters. So in this kind of model, you have something like 4 or 5 free parameters to choose. There are now models on the market which deals with something like 40 or even more model parameter, which obviously gets much closer to the kind of real observed galactic foreground. But for our purpose, it's just enough that the statistic of this foreground is similar to that of the real galaxy. We don't want to use the exact galactic foreground. We just need a kind of similar signal to check what is the influence of the foreground. And the typical thing to remove the foreground is you smooth the map by a certain filter, so you can have that as a kind of proxy of the foreground, which is then subtract from the data. Now again, you do that. So you construct here a map which is based on your cosmological signal, on your galactic foreground, and you plug in some noise reflecting the measurements errors. You take the smoothed map, you subtract, and that is what you get as the remaining signal. And that is the same when you do with the observations. So that is the signal you want to deal with. And what we did is to even go to instruments which might be so surveys which might come from future instruments. We even reduced here the noise a little bit and went to a noise level of 1 watt per square meter, which is kind of very low noise compared to the real observations. And that is the remaining map you get. So you get some remains of this foreground model subtraction plus some cosmological signal. So if you zoom here on individual galaxy clusters in that map, because we know where they are in the simulation, you can see the signal produced by the galaxy clusters. You can try to calculate the correlation function and see if you can infer some models. So when you calculate the correlation function, you have 2 ways to do that. One is a normalized correlation function, where, so to speak, the signal is then normalized to the absolute value of the signal, and you can do it in an unnormalized way, so that you don't normalize to the mean rotation measurement of the map. So both have different advantages and disadvantages. So as you can see here, when you look at the normalized function, and you have only the cosmological signal, you can quite nicely see these different models. They are different. They have this crossing as they have it before. So that is reflecting quite nicely the shape of the models. Where you have the unnormalized, the shape is a little bit lost, but given that some of the models have some higher rotation measurement, you clearly see that sticking out. Now the problem is now if you add foreground and if you add some noise, and if you add the cosmological depth of that, it turns out that this normalized one, so to speak, is heavily influenced by this galactic foreground. So the signal dies completely out due to noise and foreground. And if you take the unnormalized, then that is relatively insensitive to this foreground removal, which is good. But on the other hand, it doesn't reflect any longer your intrinsic model, and it strongly depends on the optical depth of your signal. So you get a nice signal, but the amplitude of the signal is already quite heavily washed out. And you can look that in more detail. Again, that are the correlation functions calculated from these different models after all this procedure. So you get a nice, for every of these models, independent if it's a model with low magnetic field or with high magnetic field, you get a nice correlation function which is several sigmas away from the null signal, which is a dashed line, which is just reshuffling of your data points. But the order of these models doesn't necessarily reflect any longer the strength of the magnetic field inside the models, and even worse, all the error bars in this correlation function overlap, which is other. So you get a correlation function, but it doesn't tell you anything about the magnetic field. And you can confront that with the observational claims at that time. So that was the observational claim of the correlation function here, and that is what we get from the simulation. So quite nicely to see, we get a very similar signal here with a very similar amplitude. However, the amplitude, as I told you, is the same for all these different models. And here's a cosmological magnetic field orders by several orders of magnitude. So again, it unfortunately doesn't reflect any longer the intrinsic model. It just really deflects how the errors from the foreground and from the uncertainties of the models are transported into this correlation function. But again, also it's a negative result in the sense of detection today. Future instruments which are supposed to deliver maps, as I showed before, with something like 10 or 100 times better quality, are really interesting for this kind of study. So I think at a certain point, these things has to be redone in a more sophisticated way, and we really will learn something from that. Now, as I said, there's another method to investigate magnetic fields on even larger scales. It's with trying to understand the deflection of ultra-high energy cosmic rays. Again, biggest problem here is we don't know the source, but the advantage is it's at least proportional to the magnetic field. Disadvantage is it will always measure you the largest magnetic field along the line of sight and doesn't tell you something about the average thing. So there is this Pierre Auger Observatory for ultra-high energy cosmic rays, and in 2008 they published a very nice map where they claimed that the CR correlation between the arrival directions of the ultra-high energy cosmic rays with the large-scale structure, in that case with AGNs, and that would have been a very nice signal, because then you really would identify the source at the same time, and then you can study the deflections and learn something about. Now, if you want to compare that to models, you have to take into account that these cosmic rays cannot propagate infinite distance in space. So typically the horizon is at 100 megaparsec or maybe 200, but not much more. So it's very local. So if you want to now study the signal you want to observe, you have to go to a simulation which reflects the local density, and we are in a very special environment. So there are, here's a density distribution where you see Perseus Spices, Coma, Centaurus, and all other superclusters in our local neighborhood. So you want to construct a simulation which reflects this kind of density distribution. So what you do is you can take, for example, a full sky catalog of galaxies. So that is the Iris galaxy. It's roughly 15,000 galaxies. We know the distance. They're all here selected to be within this 100 megaparsec. And you know their 3D distribution. So you can construct from this 3D distribution a density field today. You can linearly transport that back to your initial conditions and take then this information you get from this transport to constrain your initial conditions. So when you set up initial condition, you usually use a realization of a random field, but you can put constraints on that realization so to speak, face-to-face correlation by just taking the observed density field today. And if you do so, you end up with a simulation where these kind of structures of galaxy clusters really correspond to local objects. And now let's see if that is working. Yes. So that is a fly-through to this kind of simulation, where these clusters which are forming in the simulations are labeled to clusters which are real observed, and their position is within a couple of degrees correct, and their masses and properties are also within a factor of 2 as they are observed. So that's a very nice simulation you can use to study kind of local universe. So I think it's, no, that's just a rotation at redshift 0, sorry. So you can see there's a great attractor here going through Centaurus supercluster. So you can really see that these precious spices here, all this kind of local structure which you saw before, which are very peculiar for our environment. So if you would take a random cosmological box at any place, you might get very different results. So now you have the sources of cosmic rays, and you want to study the propagation till the observer. So first of all, you have to understand or to investigate what happens if this source is sitting in a galaxy cluster, because we know in a galaxy cluster magnetic fields are quite strong. So what will happen in this galaxy cluster is that the cosmic rays, even at that energy of interest, are doing this kind of scattering process. So that is a direct simulation of cosmic rays just emitted isotropically here at the center of one of the clusters in the simulation, and then you follow their deflection inside the magnetic field of the simulation, and you can see that it kind of goes on kind of this scattering track, so it can be described as kind of diffusion. It goes to larger and larger distances where the magnetic field gets smaller and smaller, and at a certain point it escapes and with not much of an deflection any longer. So what that means is that if one of these sources of the ultra-high energy cosmic rays is sitting in cluster environments, then just the whole cluster would appear as a source. Because inside the cluster you would get an isotropic distribution, and at a certain point you propagate outside. This has some interesting consequences, because when you now I take a cluster and I take a sphere around the cluster and ask how much cosmic rays are coming out at what direction, you find that depending on the energy, of course if it's very, very high energy, then the deflection is very small, so the stuff is coming out isotropically. If you go to lower and lower energies, the deflection gets more and more critical, and you get this kind of structures where along certain directions you have more cosmic rays streaming out the cluster, and in the other direction you have less cosmic rays streaming around. So now imagine that you observe this cluster from here, you will see a very high flux in cosmic rays, and if you observe it from here, you can get very low. If you then go to lower and lower energy, again, you get more and more diffusive, and you again get isotropic. So there is, in this kind of interesting window for ultra-high energy, there's a transition between either being completely isotropic to something which looks different intensity on different directions, till to the lower energy, where again you get, by all the scattering inside the cluster, you get isotropic. So that is, so to speak, something you have to keep in mind when you compare different clusters and say, okay, I observe so many cosmic rays from that cluster, but none from that. Is that a problem, or can it be related to internals of the cluster? Now then you take some cosmological simulations, and here are a couple of examples. So that is a example taken from early work of Uri et al. So that's a filament. You see the density of the filament. You see the velocity. So that is how the stuff is accreted on the filament. You have shocks here going, and you can think about some battery effects on the shock. And then this magnetic field is transported inside the filaments and amplified. So you can have some magnetic field inside the structures. And that's basically the kind of principles these kind of simulations here are based on. Or you can start from a cosmological background field and simulate your cluster. And that is, so to speak, the result here. So you can see that here the magnetic field is, of course, everywhere distributed because you have a model where you start with a magnetic field distribution everywhere. So now you can combine. Yes. Yes. So we come that on the second part of the lectures where we speak about simulation, actual simulation. So that's, I have here also only to refer to the simulation to give you a picture on what is the idea behind that, but it will be more in detail discussed in the next lectures. So again, you can look at different regions, and that is this kind of filamentary regions here in the superclusters here. That's the Centaurus supercluster, and you can look around how the magnetic field in this kind of filaments could be, just as a warning. As you see, these cosmic structures are never straight lines, nor they are real always filaments. They are also sheets and other projections, so you have to be a little bit careful. But you can study, so to speak, if you go along. That is now just taking this line here, going along, and oops, no, wrong direction, and asking what is the density. So you can see that you go through the filaments and you reach the next clusters and things like that. And the gray regions here are the virial size of the cluster. You can ask what is the magnetic field, and you can see that inside the clusters it's larger and in this void is lower. And then if you have this very extended lobe voids or filaments, you can even see that the magnetic field starts to get aligned with the direction of the field, whereas in all these realized structures there's of course no alignment at all because it's random turbulent field. If you plug slices perpendicular to these filaments, you can again see that the structure is quite complex. You have this kind of filamentary structure, but then there are sheets ending in all the time. You can look at magnetic fields here, how it is arranged around these filaments. So it's really complex geometry. And so what you have to do is you distribute your sources, and then you really integrate through the structure and calculate how much cosmic rays would be deflected. That is an example here, just taking here 4 times 10 to the 19 eV cosmic rays, which are these high energy cosmic rays, cutting out a sphere of 35 megaparsec around your observer. And that is just to emphasize again why it's important to take the correct environment. So what we have chosen here is, that is in the simulation the real position of the observer, so that's really position of our Milky Way. And we have close by, we have the Virgo cluster, which is, so to speak, the largest source of deflection with its connected filament close by. But we could, for example, go into the Centaurus supercluster region, but place the observer at a place where you are as far from the next big clusters than we are here in the Milky Way. So if you just ask, where is my largest cluster close by, these kind of two positions are identical. But as you're sitting here in a much higher density environment, you can see that your deflection is much larger and you have much more structure in front of you. So really, if you want to ask this kind of things, you sometimes have to be really more constraining with your position. So that's the reason why using here this kind of constrained realization of the local universe is really important. So then you can include losses or not. So that is an example for 10 to the 20 EV propagation. Once taking losses into account and once taking no losses into account. As you can see, with losses, the deflection goes down because you have to start with a much higher energy to reach with the same energy as the observer. So at the beginning, the deflection is much less. But again, it's a small effect, so it's not really essential, but it has some effect. So that is now just as an example, one of the simulations. The signal you would expect for 4 times 10 to the 19 EV cosmic ray protons. And you can see that you get some deflection of these filaments. And of course, if it would be exactly behind a galaxy cluster, it would be deflected much stronger, and the whole galaxy cluster would be looking like a source. You can now do that for different models of the magnetic field, as discussed before. And what you can then produce is not only the deflection map, but you can also ask the question, what fraction of the sky is covered by deflection which is larger than a certain amount, so typically larger than what your resolution of your instrument is. And you can see that even with the high magnetic field case here still, if you look at 1 degree, half of the sky would be transparent to that. So in half of the sky you would be still being able to point back to the source. For these galactic outflow models here, which have very low magnetic field as a large-scale structure, it's even much more sky which is free of any significant deflection. So basically, just from these kind of models, you would assume that if the cosmic ray, high-energy cosmic rays are really protons, and that is something which currently gets challenged, but if they are protons, you should be able to point back to the sources. Again, that's just to zoom in on these kind of deflections, just to show you again what is the difference between the different magnetic field models. Now you can do again that for all the different models which were discussed before, and you get different deflection, and you can try to challenge that against observations. But that's not end of the story. So you not only get deflection by the large-scale structure, but you also get deflection by the local Milky Way, and that can be significant. So at the end of the day, you want really to construct a full tracking approach. You take your cosmological simulation, you place your sources according to a model for the sources, you follow lots of tracks and select these tracks which end at the observer position of the Earth. You fold it through the deflection caused by our galaxy, and if you do so, you have two further observables which you can check. So first, if you do it at different energies, so here's plotted always the arrival direction of different energies, and you can see you get this kind of tracks from individual sources. So depending on the energy, you have a different deflection inside the simulation. So if you then go for example, doing kind of position energy correlations, you can get even more information out of these models. And second of that, if you include all the loss processes during this tracking here, you can also ask about the shape of the spectrum. So you put in some spectrum of the source, and you get out a spectrum of the arrival protons, and can compare that. And again, that is ongoing work, and currently it's still in progress. But the basic idea is that you can use these kind of models to constrain magnetic fields. Now, there is, as I said, this correlation of arrival direction with a large-scale structure claimed by Auger. Unfortunately, since 2008, the number of events really went up, which is good, but the significance of the signal went down, which is bad. And since many years now, it's at roughly 3 sigma level, not fully 3 sigma 2.7, but it stays there. So it's a very puzzling signal, because if it would be something, if we would have stayed up there or even rising as you would have expected, you could start to derive really stringent constraints on magnetic field. But as the signal itself, it's still questionable. If it's true, it's very difficult to constrain magnetic fields from that yet. But again, next generation, hopefully, of instrument will help, and also say working on kind of energy calibration, which is a very difficult task here, and will help to constrain that. So again, there is a correlation. So this signal is not really isotropic at the highest energies, but the strength of the signal is still under heavy discussion. So it will take a while until we can really make use of this kind of data. So as I said, there's another way to constrain magnetic fields in large-scale structure, and that has to do with these TV gamma ray photons, which do an electromagnetic cascade, which gets deflected. So in the first case, you would expect that this lower energy cosmic gamma rays, which are reaching you, could build an halo around an observed object. And if you want to simulate that, then you have to do this tracking, and you might have even several of these cascades you want to follow. You can make it as complex as you do. And indeed, there was a very interesting result claimed, namely stacking of 170 AGNs with the Fermi instrument. You find that you get this kind of extended extended tails, which depends on energy. And here the claim was that the red line is the point spec function of the instrument, so you would really see an extended tail, and that would correspond to this kind of blue halo at that energy and that blue halo at that energy, so you can compare a kind of simulation to the observation, and you would claim. And if you take that observation seriously, you came up that the magnetic field mean magnetic field along the along the line of sights, so in the voids and so on, has to be 10 to the minus 15. So if you really detect a halo, that's giving you even a number for the magnetic field, not just a limit. You can do that with our simulations. So we took some line of sights from our simulations. We calculated the deflections, and that is the kind of halo which we would expect. And again, as you saw, it's very, very similar to here. It's very similar to what is observed. Unfortunately, the paper is heavily questioned, which detected that halo, because that seems to be an imperfect handling of the point-back function. So unfortunately, the signal can be completely explained with using a more proper modeling of the point-back function of the instrument. But still, so to speak, this would be one of the interesting detection if at a certain point one would really see a signal. Now, the mapping then is, so to speak, if you see a halo, then it depends on more parameters than just the magnetic field. So it depends on, for example, the inclination of the jet towards you and on the time delay. And that is a very interesting parametric study. So that is your point function here of your AGN. And then you increase the magnetic field, and you can see how on the sky your halo would be orientated. So depending on the magnetic field, in increasing magnetic field, you will see larger and larger low-energy cosmic ray halo around your source. Unfortunately, you get a very similar signal when you incline your jet. So of course, you need a magnetic field, but so to speak, that is degenerated. If you then also include a time delay, that the photons with different energies come at different times, then you would get even a shift. But that you can nicely distinguish from the other things. But here between the jet orientation and the magnetic fields, there's some degeneration. So if you at the end really detect the signal, it will be a little bit more complicated to interpret that in a magnetic field. But still, it would be within this kind of jet inclination, which you can infer from other properties, would give you some interesting numbers. Now, the last thing here is that, as I said, this electromagnetic cascade can also happen to this gamma rays, which would directly reach the observer, and then depending on the deflection here, the secondary are reaching the observers or are scattered out of the way. So they are somewhat attenuated depending on the magnetic field. And again, you can look how that would look like. So here you have Hess data, and you select some sources which have a very steep spectrum here. So you can calculate what you would expect as a spectrum here towards the lower tails. And that then depends on how much magnetic field is in your way, which is then, so to speak, deflecting out your secondaries out of the way. And then you have some limits of Fermi here, for example, for that source. And obviously your curve here has to stay below this limit, so you can get a kind of limit on the magnetic field, forcing your spectrum to stay below the measurements. And as I said, the interesting thing on this last method is that it depends really on the deflection of the cascade all along the way. So if a part of the way is not filled by magnetic field, it will completely destroy your signal. So you can not only get some limits on a value of the magnetic field, but also on the filling factor. So, for example, you can, if you do this kind of very simplified model, you find that at least 40 or 50% of the line of sight has to be filled by these kind of values. If you fill less of that volume with magnetic field, you can increase it to whatever value you want. You never get this kind of attenuation signal. So that's a really extreme important probe, because it's not only probing a magnetic field value, but also a filling factor, so which is a very nice part of that game. And again, you can compare that with some cosmological models, and you can see that, for example, some primordial model here will also always have enough magnetic fields in the voids to produce the correct spectra. But if you go to these old galaxy outflow models, where you really have the magnetic field concentrated in the structures, you already start to challenge here the data. So again, that is telling you something about if magnetic field is coming from the galaxies, you need some mechanism to transport it out of the galaxies, which is not included in these simulations yet. So again, it's very interesting, because it's giving you really deep constraints on these things. Now, last point to mention is that recently there was a paper that found the first two high-energy neutrinos, which are cosmological. And again, as I read today, which I wasn't aware, there should be much more of these guys now. And the interesting thing is that you can ask how much neutrinos you expect from all these processes I discussed before. And if you take some kind of very simple models here, you see that you're not so far off from the signal. So again, that gives you a kind of complete independent measurement of all these processes. So you can make, again, trying to do a kind of consistent picture, combining all these different processes, because you now even can include the neutrino signal. Now, as a summary, again, what I wanted to discuss in this kind of lecture is constraints on magnetic fields on even larger scales than galaxy cluster. And again, to repeat, because I think it's very important, rotation measurement, as you saw, are very good in galaxy clusters. You can constrain a lot of things in galaxies and in high-density regions in general. If you go to filaments, there's the hopes that extending these things to statistical methods can probe slightly smaller magnetic fields. But again, so far no success. So we need better data, but they will surely come. If you take cosmic charged particles, ultra-high-energy cosmic rays propagation, you would probe magnetic fields which are here somewhere in filaments. And these kind of structures, again, looks quite promising, but current data are still don't allow very strong conclusions. So also here we will have to wait for new data and more data. And TV gamma rays really recently opened a completely new window to magnetic fields on very large scale, with some very promising results, especially the one of the spectra. So here we really learn something about magnetic fields in very dense region. Right, so that is the same I said before, just in words. And again, it's a strongly growing field of research. So anyone who is interested, I can only encourage to either observationally or simulation-based join this kind of fields. It's really something which, if you look on recent publication rates and papers, it's really growing within the last years, and it's very promising. There are many instruments coming online, and many more data will be available. So that's really kind of very future field. So I just can encourage you to join this kind of efforts. So I stop here for questions. Yeah. Especially if you think about this kind of voids where next galaxy is several megaparsec away, it's not trivial to propagate magnetic fields into that. But still, there are interesting models which concern streaming of cosmic rays, which transport magnetic field, which might be even able to fill the voids. However, that has not done very deeply. And then, of course, if that doesn't work, then the only way to get magnetic fields there is from primordial fields, yeah. That's the reason why this void stuff is so interesting, because it's... We don't know. So if you take the limits we have from rotation measurement, so to speak, which are very weak, the magnetic field can be as high as dynamically important. But as we haven't detected them, it's purely speculation. Yes. No. But again, that is, so to speak, the minimum magnetic field spread over. That doesn't exclude that in a filament the magnetic field is 10 to the minus 8, which would be exploding filaments magnetically. So again, especially for filaments, for that kind of density region, we have no measurement which is telling us exactly a magnetic field value. We have some measurements from these very large scales which start to give lower limits. And if you plug in these lower limits into frozen-in conditions, then we would conclude that void is roughly mean density. Filament is, let's be very, very generous, it's 100 above the mean density, so frozen-in would mean that you only amplify that thing by 1.5 magnitudes or something like that, so it would be still very small. But we don't know. It might be that this kind of shocks on the filaments are driving very complex plasma dynamics and plasma instabilities and amplifying the magnetic field. So basically no. If, for example, like in the first lecture, if this magnetic fields in these relics is really 7 microgauss, that is really challenging, because these values at that large distance of the cluster, again, are in a range where dynamically they would be important. So... Or they are very local. They are something like within hundreds of megaparsecs so far, because you need high flux. And you need some sources which are very stable, which have very steep spectrum, because if it's very flat spectrum, you don't learn anything. So that is reducing the number. And then you need sources which don't have a big time delay. I haven't mentioned that. But of course, when you look at this spectral stuff here, here, of course, these things have different travel times than these things. So if that gets of order of the time delay, you would expect of the, not time delay, of the variability of the source. So if the time delay between these photons and that photons are of the order of the variability of the source, then again, you cannot draw any conclusions. So that's a big caveat. So you have really to look for sources which look very stable, which have steep spectra. So I think at the moment, people use of order 5-ish sources which fulfill that criteria.